Okay, we're live.
Okay. Hi, everyone. Welcome to another Wolfram Institute live science stream. We're continuing our conversation with Richard Assar about moduli spaces of graphons of causal graphs. It's a way to parameterize spatially the kind of computations that we do. So, Richard, I think since we had our last stream, we've been discussing a number of things. There are a number of kind of basic updates to share.
All
Um,
right.
I think it's kind of up to your discretion how we begin. What do you want to show first? What do you want to discuss? And by the way,
Cool.
everyone, apologies for the belated beginning of this stream. There were some technical difficulties, et cetera, et cetera. So for those of you who waited, um, yeah, we owe you.
A pizza.
Yeah,
Okay.
yeah,
All right. So everything was kind of being shuffled into this report structure.
yeah.
So I guess like going over that will give us some talking points, and then I have some things that I'm in the middle of looking at. These are these terminating systems where we sort of increase the size of the initial state in order to get bigger and bigger causal graphs. But let's I mean, is there any point in me just sort of reading out what I've written? I don't think so. So
No,
I wonder what
this
you
is the
think. Yeah.
problem with these streams. Like, yes, would it be good to provide a summary of what it is every time? Well, yes, for the new viewer, that would be convenient. But I tried doing that when we first launched the Institute, and it turned out like it would take like
Yeah.
15 minutes every single time. So
And this is a
let's
shorter one.
let's
So yeah,
let's
let's
just
just
jump right into it. Yeah.
yeah. So some of the recent things I've done is looking at like a graph growing process. So by sort of applying one edit operation at a time, we can build this structure. And when we equivalence with isomorphism or apply transitive reduction, which further matches the structure of our causal graphs, we end up with this kind of interesting structure, which I don't think has kind of been explored or discussed before. So this is sort of like a finite presentation of what this moduli space of graphons, or the infinite limit of some graph process would look like. So the initial arrow here is the empty graph, and then down this path is just adding a new vertex. And then anytime you deviate off this path, you're adding an edge, adding a vertex, and you're adding a non-existent edge already. So
So
this is the
wait.
under yeah.
So one step at a time. So the red
Mhm.
arrows
Yeah,
are vertex additions.
vertices. Yeah.
The green arrows are.
Mhm. Or the not red are edges. Yeah.
But what's the difference between the blue and the green and the
Oh,
and
it's
the
just
light blue and the pink?
there's no the only consistency is just to do with which the order of the edge. So I mean there will be some consistency. It just depends on. So if you look at the underlying code, we're basically building a sort of list of successor states where we take the current graph and add a vertex, or we take the current graph and add a previously non-existent edge. So the color really corresponds to the position in this list of future states. So the reason that red is always vertex is because it's always the first one. That's how I build this list of future
Yeah.
states. And blue presumably will just be the first available edge that can be added, and so forth. So yeah, but this is, I mean, you could study this object in many different ways, but it's more just as a sort of explanatory tool, just to say, like, we have this space of graphs. They're all one operation apart from each other, and they exist in this structure. And when we add constraints, the sort of behavior of the structure changes. So this is undirected, this is directed, and this is directed with transitive reduction. So you can see it becomes a lot more sort of tangled and interesting in the transitive reduction case.
Yeah.
And
I don't know what to make of it though. It's very
yeah.
interesting. It's a very good idea
Hmm.
to to kind of generate. The question is, can you kind of generate a moduli space? In this case, it's not just okay. So this is quite different though from the moduli space of graphons because this doesn't just include limiting objects. This includes effectively all transitively reduced DAGs. This
Finite
this little
DAGs, yeah.
this one at the bottom, finite. finite
Hmm.
transitively reduced DAGs,
Hmm. Yeah, and they're
FTR DAGs.
yeah, and they're sort of equivalents up to relabeling or isomorphism, whatever you want to call it.
Yes,
So each
yes.
vertex is, I mean, because essentially a graph is an equivalence class in itself. A glass, sorry, I lost my ability to speak. A graph is an equivalence class of all other graphs isomorphic to it. So each vertex in this structure here is an equivalence class, and yeah, as it grows and grows and grows, it's well, it definitely doesn't have a trivial structure, that's for sure. It very quickly gets into sort of a lot of complicated things, and
So
we could study that.
you
Yeah,
yeah, I mean, so you ran this for how many steps is that? Like
let me
three?
see. Let me see. 7
Oh,
on this
seven.
one. Yeah, I don't know how many on the others. So not many. Just didn't want my computer to
Yeah.
freak out too much. And it's more as a sort of illustration. It's like because I mean it's a little bit difficult to think of a continuous space of sort of
Yeah.
deforming graphons. So it's more as an explanatory. Like here you go. Here's what it looks like in the finite case. So this is our sort of big bang, and then some sort of universe of graphs starts growing in the sort of future of this in this direction.
Yeah, I mean, so this is a nice start. I would like to see hmm, what we can do further with this. If we can run
Mhm.
it for more steps, and if there are kind of properties of this graph that we
Yeah,
can actually query.
yeah, yeah. It would be nice to
Mm,
study it, but initially it's explanatory. Also, another reason for doing it is performance, because the edit distance thing that I did on this was like an overnight thing, and it's kind of a waste. Because in this graph, if you take two graphs
hmm
and you locate them in this graph and then find the shortest path, now you've computed the edit distance and you didn't have to do this complicated search procedure. It's almost
Yes,
like
yeah.
when people crack passwords, they pre-generate these things called rainbow tables so they can do quick lookups. It's the same idea that if you were to pre-generate this structure here, and then you take two graphs, locate them in this thing, that the shortest path, the number of steps in that path is the minimum cost edit distance in any direction, because going backwards would be deletions, going forward would be additions. So it's also performance kind of, because yeah, this thing took a long time to run,
Yes, yes.
in order to get this distance matrix, and then yeah, we embed that to have this neighborhood. I will remove these numbers so that it's and actually make the call out. I had to do it by hand in a separate application because I'm still learning the sort of graphics functionality of Mathematica. So yeah, that was that. We've already covered this sprinkling thing before, where we fit the function to this um, parameterized manifold, and so we end up with a sort of graphon.
Well, before
Yeah.
I mean, let's just go back to this generated graph that you
Oh,
produced with
the,
NestGraph tag.
okay.
Let's try and determine concretely some next steps for
Okay.
this thing.
Sounds good.
Hmm. Would you mind actually rotating it just like
Oh, yeah, for sure. Yeah. Actually,
because it's
I often want
yeah,
to do this when I'm taking screenshots, but like, yeah, I could generate video.
just trying to get a sense of what this thing looks like.
Yeah, this one's a bit tangled. Maybe this one, the undirected, not transitively reduced case.
There's a thing you can do, by the way, which is well, yeah, okay, we'll figure that out later.
I have created GIFs before where you move the camera around, but what happens is it sort of automatically reframes the camera in this really annoying way. So I don't quite know how to do it in a nice way where the camera doesn't fit the view frustum around the extreme of the scene kind of thing. Anyway, so yeah, that's what you have here. You have something that sort of starts off kind of quite linear, planar, and then starts going into this branching thing.
Well, it's always hard to tell because those kind of frayed ends, I was trying to look it up. I can't find it. There's some way that you can remove the loose ends from these graphs, because
Oh,
sometimes,
yeah, no, actually, in Stephen's multi-computation on numbers paper, he does it with the callouts graph because it has a lot of dangling ends, and he removes them
yeah,
and just leaves the thing. So
yes,
probably the click to copy has how he did that there. So yeah, we could also look at that.
yes, I looked it up. There's actually a click to copy problem in that blog that I reported yesterday. But
Right,
in
right.
principle, you should be able to get the code.
I've
Yeah.
been trying, and I always think, oh, is it just Chrome? But no, it seems there's problems. So this one is kind of almost similar to the previous one, but instead of starting off with that kind of plane, it's sort of like four different. Anyway, these are not really meaningful as
Well, I mean,
conservation.
I guess the question is, I mean, even if you take this one, there's
Mhm.
like, yeah, if you maybe pause, I'll highlight something. Yeah,
Okay.
maybe just right there. Yeah. Okay. So, I mean, you see here, for instance, here, you could have some edge that goes between these, but you
Hmm.
don't. You have a
Hmm.
little kind of hole there. And the
Yeah.
question is, like, based on how you're generating this graph, do we expect that hole to ever be filled? Or because you're kind of starting with the empty graph and you are proceeding outward, if there
Yeah.
are holes that emerge like this, can we presume safely that this is just going to be a little hole that's not going to actually be filled?
There's a vertex budget. Like once you've exhausted it, you can't. You need more vertices before you start adding edges. So that's
Yes.
probably why that hole exists. Maybe I don't know in this case. Like it maybe ran out of vertices and there were no more, or yeah, there was only one edge it could add. Actually, no, because it goes here and then off. So, it'd be nice to be able to hover over and actually see the graph as a call out and like, oh,
Oh
yeah,
yeah, you should just be able to tooltip it.
yeah, okay.
Yeah. Callouts, Nick, you correct me if I'm wrong. I mean, callouts you usually specify, right, Nick? But tooltips,
Well,
I can't remember
callouts
the
are
difference.
just the actual graphics on top of the graphics, just pointing
Yeah.
to the actual vertex. And tooltip requires you to mouse over it. That's the difference.
Right. So the call out will actually, but you have to pick them specifically. You have to choose which ones are called out, and then it'll actually be included in the image. Tooltips are, I think, more flexible, especially if you don't actually want it to be shown. You just want to be able to query the vertex.
If there are any good examples of that, then yeah,
What
please
of
point me.
tooltips?
Of well, yeah, both callouts and tooltips. Yeah.
Or just
Well,
go look at the documentation for callout and tooltip.
Okay.
I think that's a straightforward way of
but
finding some examples.
Yeah, but within Nest Graph Tag, like how to.
Oh, within graphs, well, you just have to modify the shape function, or
Okay.
I don't think it depends whether the graph itself supports callouts and somehow specially. I don't think it is actually. It's like, callouts are well supported in some plotting functions when you have some special line plots or surfaces.
we've had graphs with tooltips quite
Well,
often.
tooltips is pretty easy to set up.
Yeah.
It's just a label with a tooltip. If you set a label for a vertex that has a tooltip, it's just gonna be it's gonna just show up on the mouse over, and that's it.
And when we publish this thing to the web, it would be nice to have that
Callouts.
interactivity if it's possible. But I mean, yeah,
Tooltip should work.
That's even better. That's even better. Yeah, yeah. Right.
yeah.
By the way, I mean, Nick, I don't know what your comments are on it. Sometimes I find that there are things that I'd like Nestgraph tag to do, like especially in terms of styling that it can't do, and then I just have to use Nestgraph. Nestgraph seems more flexible, more accommodating, but I'm not sure. Maybe
I don't know.
it,
It's just a graph. How more accommodating it can be. This is also a graph.
Yeah, exactly.
You can use the same options for it. So I don't know.
I've found like design options, for instance, where it wouldn't let me do it for Nestgraph tag. I had to take it down to Nestgraph for whatever reason.
Yeah, okay.
So yeah, so that's, I mean, that's kind of a key, this question that I was asking before about the whole, I think that's a kind of a key question, which is if there's some, if this graph is okay, well, I guess in this in the non-transitively reduced case, it's kind of the graph is kind of expanding outward. And so when it's expanding outward, you're kind of led to presume that if there are any non-trivial topological features, like a hole, that nothing is going to come back and sew up that hole. And the question is that an artifact of the way in which it's been generated, or is that some actual property that's of interest in this kind of generated moduli space? In the transitively reduced case, was I gathering? Oh,
I'm just running this for more steps whilst you're talking to add some visual, and also to see if anything interesting does happen at a larger number of steps.
Sure.
Yeah. So sorry.
Yeah, and were you suggesting, Richard, that in the transitively reduced case, that it's not just this outward expansion? You have some arrows coming back, et cetera, et cetera. So in that case too, yeah, basically in either of these cases, I'd like to know, is this used kind of just for expository purposes where we shouldn't take the graph structure too seriously?
The question is,
what do we do with this?
Is it just branching, or is there any sort of? I think there are interesting things going on. It's just kind of hidden, and looking at the community structure and cliques and things like that would be better. And the transitively reduced thing seems to, it doesn't branch in the same way. Everything is kind of collapsed back into central structure.
Yeah, it'd be good to see what that one looks, how that evolves with time. And yeah, kind of the key question is there topological structure that is kind of an artifact of the way that we're performing these rule applications?
Mm-hmm.
Where, as you said, it's like, oh, we needed a vertex. The vertex wasn't created in time, and so there were some constraints on the actual applications of the rules.
And then the other question I would say is in the space of like in the space of all wait,
how do we interpret this?
So in the space of all computational system causal graphs, is the set of all transitively reduced directed graphs, are they the same, or is there some sort of subset of that set of all graphs for in the computational case? Like, does the computational case not generate all possible directed transitively reduced graphs?
Yes, right. That's another key question. Nick, do you have a take on that?
On the existence case of those computations that can generate, or what?
Like, is it possible to generate every possible causal graph? Like, is it trivial to just construct a system that will generate any given causal graph that you want? Yeah. And so that means that the set of all computational causal graphs is exactly the set of all transitively reduced DAGs. Is there the same thing?
That's basically asking, is it the case that there's a particular TR DAG, I don't know what we need to call these, transitively reduced DAGs, that no computation, for which there's no computation with that causal graph? It seems highly unlikely that there would be some special TR DAG.
Or that there is some pocket of impossible to produce DAGs that you could never produce computationally.
Mm-hmm.
Like, could you define?
Yeah, that's what I mean. Right.
Right. Okay.
It
seems unlikely.
How reducible it is. If you just given a random causal graph, it may be like there is no actual computation that produces it with some smaller complexity than the graph itself.
Yeah. Exactly. Yeah. The very Kolmogorov type analysis. Yeah. Okay.
Now, what are you looking for in these histograms?
I don't know. I'm just looking at the vertex degree histogram to see if there's anything. It just seems there's a few things you could do to, yeah, what is this really telling us? I don't know.
What was the adjacency
Yeah, that
matrix telling us?
was. Mm,
I hadn't seen one
I'll
that looked
do.
at, I don't
I mean,
know.
it's like kind of non-trivial. It's not tree-like. It's yeah. And these should be the vertices should be ordered by like the generation number in which they were produced. So it's yeah, it's a fairly sensible. I mean, one reason I was playing with the numerical multi-way systems is that you can sort of sort the vertices by their actual number, and that gives you a decent ordering. But in the graphon consideration, we don't care about ordering because they're all the same. It doesn't matter how you order the vertices. So let me see. What should I do? Should I just go further with this? I don't know. Hmm.
Is there, by the way, some continuous notion of not caring about ordering? If you just handle
Mhm.
the graph on an interval from 0 to 1, what does it mean don't, that you don't care how like points ordered on this interval?
Yeah, that's in the. Let me go back to the other one. Uh, where is it defined? Have I put it in here? Yeah. So like
The cut norm, right?
yeah. So it's like every sort of it's like over all possible bijections on the unit interval, which is yeah, every permutation possible. Which is yeah, completely intractable to compute in any sense, but we're talking about like
Just
the infinite
it's kind of
case.
property of some function, right, on the
Hmm.
interval, not of the
Yeah.
interval itself.
Hmm. Exactly. Yeah, it's a property of the function, but because your parameters are sort of bounded in this domain, then you can remap the domain. You could instead of x, you could have 1 minus x, or you could mirror two halves of it, or you can do all sorts of
Mm-hmm.
things. As long as it's a bijection, then yeah, and then you do it over all possible measure preserving bijections, and then yeah, it's supremum over that. And yeah, that gives you that's the continuous notion of graph on distance, which is what we're using to basically say that two graphons are equal. Um, yeah, that's the equivalence relation.
So we might not determine a formal method over the course of this particular live stream, um, a method for actually analyzing this graph that you've
Mhm.
generated, but it does highlight some greater problems, really, if you take the example of the nest graph tag example that you showed, which is, again, it's like you generate some particular graph, either using multi-way system or nest graph tag, et cetera, et cetera. You have some complicated graph. I would say at the moment, we don't really have, unless I'm forgetting some things, some rigorous ways of really studying the properties of these graphs. Like,
Mhm.
it's like, okay, let's take a look at the array plot of the adjacency matrix or the graph design. I
Sure,
mean,
sure,
you
sure.
can
I
you
mean,
can look at
exactly.
them and
Yeah,
we have heuristics, but it's like, if we're going to study like the topology of these things, do we
Mhm,
have
mhm.
some efficient way of actually querying some of these properties?
Yeah,
I would say at the
there's
moment we don't really have anything beyond using pretty rudimentary tools in Mathematica along with
mhm.
some kind of heuristics like, oh, this looks like this other case. As you said, this doesn't look tree-like. This has
Yeah,
the some non so yeah, we can use these heuristics to kind of just sort these into kind of classes of, okay, this is not like a tree case, this is something different, but we don't have stronger we don't really have, this is just a general problem, I would say. We don't really
sure.
have good ways to study the kind of the topology of these,
There are
though
like
that be
spectral, yeah. There's like
okay. Go
spectral
ahead.
methods and so forth, and we can look at implementing, and not just implementing them, but understanding how to use them and interpret them. It's not just like, oh, here's something, let's implement it and use it. We have to actually understand what it means and what it's saying. So we have
Yeah.
to build up our own sort of experience with it. And yeah,
Understanding is good.
there's a bunch of tools that I want to explore. I've spoken about a few times, which is this Stanford. Let me just click this. This whole package here is graph or network analysis and graph mining library, and it's got a bunch of stuff. One of them being like the fractal. They call it Kronecker graph parameter estimation. So a bunch of these I want to work with. So we just have to take our graphs, spit them out in some format that this thing accepts, run these tools, and see what happens. And but yeah, one of the interesting things when I was doing study, so there hasn't really been a kind of comprehensive study of like multi-way systems on sort of the computational linguistics side of things, where Chomsky and there's the extended Chomsky hierarchy, and there's a bunch of other things.
Sure.
I've put these in separate cells. Whoops. Oh well, we'll merge them another time. But we have different automata for recognizing sentences in various languages, from finite state to non-deterministic, push down, bounded Turing, and then just Turing. And that was quite an interesting thing to look at, because you get these very trivial structures from the regular grammars, slightly more complicated in the case of something like this palindrome generating thing. Again, regular is quite simple. This is through Morse, where I think this one does terminate, or does it? No, sorry, no, doesn't terminate.
What was that? What's that thing you have just above there? You changed the initial state to.
That's correct. I was looking at larger and larger initial states. So initially, I just start with 0, and I start going to like larger and larger.
But what does the graph on? What is the graph on for something like this?
Yeah, because that's another thing, is like we usually think about just running more steps, but as you increase the size of the initial state, the causal graph also gets more complicated. So it's another thing to think about.
Yes.
And you can see that this actually does have what looks like to be a kind of a density that varies over the adjacency matrix.
I know. So actually, this brings up, if you don't mind, this brings up a general question I have about graphons that I was asking you a few days ago, which is usually when I see these graphons that have been extrapolated to the limiting smooth case, I've only seen so many different kinds. You have one where it's like all dark in one corner, and then it gets lighter when you get to the other corner, right? You see ones where they're light in both corners and it gets darker towards the middle. And there are only so many of these that I've seen.
Yeah.
And I haven't seen ones that are like, if you take an example of this one, where it's like there's a patch here that's dark, and then it gets slightly lighter, and then I've never seen kind of ones with complicated patterns. And I'm wondering, just because I haven't kind of surveyed the library thorough enough, I don't understand with these ones that have when we look at these matrices that have more elaborate behavior, what happens in the limit? Is it a sign of kind of randomness that tends towards the uniform graphon? Is it that there are only so many limiting cases that we can actually tend towards? Do those limiting cases really deform into one another? And if so, how? I mean, these are some kind of basic questions about, so, we want to know, for instance, what does the moduli space of graphons look like? And then, there'll be some subset of graphons that are ones that you actually get from the kinds of computations that we're doing. But I feel as though I don't even have strong intuitions about what the moduli space of graphons really looks like. And it pertains largely to I've only seen so many examples of these graphons in the limit. And I'm trying to understand, are there these traps where as you try and as the adjacency matrices become kind of more elaborate, you kind of fall into the empty graphon, or you fall into the uniform graphon. These are these kind of like sinks that you tend towards once they get too complicated. So this is something that I'd like to understand, right?
I have a few things to say about that. I mean, the recent quotes I had put in the Discord, which would be under here. So
yeah, okay.
So let's see. So one second. So this is about sort of renormalizing. So this is from the paper that deals with sparse graphons, and they have this idea
yes,
about
yes,
yeah, exactly, yeah. So
yes,
this one needs to
right.
be studied a bit more.
Yeah.
It says in the classical theory of graph convergence, such a sequence will converge to the zero graphon
Yeah.
whenever the sequence is
Yes.
sparse. We resolve the
Exactly.
difficulty by rescaling the input arguments of the step function so as to get the stretched graphon.
Oh God.
Satisfies well, so and then this talks about this measure rescaling idea.
Oh,
I think
boy.
Łukasz had some things to say on that also. So, I mean, yeah, exactly. We were talking about complicated behavior, but we had never actually found one. And I did find one. So this is for the context-sensitive grammar, which produces strings of the form AN, BN, CN. So that's, like we have three A's, three B's, three C's, which you can see on this leaf node here. I think you can see my mouse cursor.
Yeah,
So,
yeah,
and
yeah.
that produces this causal graph, which is, I think we've seen in other contexts, Turing machine, I don't know, or cellular, I don't know, but the physics technical introduction has a causal graph which looks kind of like this. I think it has this thing, but yeah, this one actually has what sort of looks like Sierpinski triangle, and I'd never seen one before. So, and as you increase the number of steps, this structure here doesn't
It
get
becomes more
disturbed.
pronounced. Yeah.
It's more
Okay.
pronounced and it's kind of stable. So it's kind of interesting. Like, what does it even mean that the limiting behavior? It would be nice to try and have one that makes a clean like this. Like, it would be nice to try and find a streamer out system or something which produces this, and then we can start asking like, what does it mean that the causal graph has this scale invariance property where the subtle behavior and the large scale behavior have these connections or similarities.
But how can
it
those
exists.
patterns be graphons if they like if you can permute all of the vertices? It's like,
Well, it's just that, like, not. So when you permute, you're permuting the vertices. So it. I mean, I can try and show you an example. If you take a graph, show the adjacency matrix, and now start looking at all permutations of the vertices. I did that in one of my notebooks. It's not just simply swapping rows. It's like you have to swap on both dimensions.
yeah, rows and columns.
Yeah.
Rows and columns.
Yeah.
So you don't get. So from a given matrix, you don't get every possible matrix. So it's like there is at least. So not you can't just take a random adjacency matrix and permute it and say, oh look, it has a fractal structure. It's like it's only going to exist for one given permutation sometimes if that connectivity structure is
I
even
think
there.
Nick's question though is if you permute it, are you gonna lose those Sierpinski
No,
gaskets?
it's just that it's been hidden and from you and you know.
But isn't it? It's kind of weird. Are you saying that you only allowed to find one
You only
graphon
need to
with a
find
pattern?
one.
You need to find one with a pattern, and you can say that you've constructed something valuable.
But does it? I mean, yeah. I guess to phrase maybe a supplemental question is like you have a adjacency matrix. It looks kind of sparse, but then under permutation, you manage to find a permutation that gives something that's not sparse and seems to hold in the limit. Is your interpretation, Richard, that is a persistent structure, but you simply didn't see it under those other permutations. But under the right permutation, you can actually identify that persistent structure. And then if you take that permutation and you take its graphon, if it's really persistent, it'll show up in the limit. Is that the idea?
I think so.
It's like ultimately asking for what would be the reducible permutation that can lead to a nice limiting behavior, right?
Yeah.
Whether it exists or not.
Yeah.
Still trying to understand this kind of these kinds of graphons that we can expect. I mean, empty graphon, uniform graphon, fine. Certain kinds of obvious graphons that we've seen in the literature, where you have something persist, like you have kind of concentration in the corner that kind of persists. And then have we kind of confirmed, Richard, in the literature that these kind of self-similar patterns hold in the limit?
Well,
If we
actually,
confirm, if we
the
confirm this,
literature, there is no literature on computational causal graph.
well,
You know,
no, no,
exactly.
no, of course not.
It's
No,
like
but I
completely
just mean,
new territory.
but is there? I thought you had shared something in the past that dealt with graphons for adjacency matrices that show this kind of self-similar structure, at least theoretically.
Oh, right.
Or is that
Yeah. That's the Kronecker graph thing, but it doesn't go to.
so? Is this
They don't
is
take
this an
this.
empty? Go ahead.
It would be if unless you do this trick of um, changing the sort of so at each level, you know, the example Wukash gave about changing the measure at each level so that it doesn't end up converging to measure zero.
But the question is, if you apply this, this is the kind of the rescaling
Rescaling, yeah.
technique for the stretched graphons you were. So the question is,
Mhm.
if you apply that in general, can you, take some arbitrary one, like maybe not so
Well,
interesting,
also the other thing to
but
think about. Wait, I want to make a point, which is
yeah,
so the
go ahead. Yeah.
box counting is a method you can use for sort of looking at fractal self-similarity in a sort of, you know, if you have a space. So you know, you can take like the coastline of whatever the UK, that's the usual example they give, and then
Yeah,
they do this box counting thing, and you can find the fractal dimension. And actually, when I do it for the case that I build down here, I get like decent numbers. But when I do it on this adjacency matrix, it's sort of very close to 1.999. So it's showing you that this technique is actually not good at all, which is exactly why I'm looking at things which are graph centric. Like we want to look at graph self similarity. That again, it's like the adjacency matrix is just one perspective, and that Stanford network analysis, you know, package. It's really looking at things from graphs as first class citizens, not like, oh, let's look at the adjacency matrix and do fractal dimension estimation directly on the adjacency matrix. So yeah, I want to start looking, because yeah, that removes this question of permutation and so forth. We just look at the graph self similarity, which yeah, again is this Kronecker idea. So what they do is they kind of estimate some matrix which you Kronecker product with itself over and over again a few times in order to generate the graph. So we would end up with some matrix that, yeah, when we do Kronecker product iteratively, it would approximate the graphs that we produce up to as good as their algorithms perform. And I think that would be a much more interesting analysis than doing this box counting thing. But anyway, I mean, it's like, you know, I found one, and we only postulated that these things exist, but they do. Other things I was trying
But
was like,
how do you? I mean, the language so far has been kind of. It appears as though they exist, et cetera, et cetera. How do we move beyond that to? How would you establish rigorously that that thing is self-similar and persists asymptotically?
I think you would need to construct something that's going to behave like this in the limit, and I haven't really thought about how to do that.
I have a broader question, which is if you take this measure rescaling that you might be able to use to kind of rescue these self-similar structures from the void, from the empty graphon, if you were to use that for those, could you could you kind of protect any graphon from any arbitrarily sparse graphon from the empty graphon? Because if that's true, it makes the moduli space either more complicated or more rich, depending on how you want to describe it. This has been my concern, right? It's like if most of these are gonna get collapsed in the limit into the empty graphon or the uniform graphon, then you have empty graphon, uniform graphon, and you'll have a few, I don't know how many graphons that are distinct, and it's not clear how much they can deform into one another.
Yeah.
And yeah,
I mean,
so this
I
is
should actually, we should try
yeah.
sort of computationally sort of carrying out some of these. So they see here, they rescale the height, like the value of the function, or they rescale the domain in order to keep it, occupying the whole interval. So we should actually sort of
Are those gonna
try these.
correspond? Are those gonna correspond to some kind of uh, fine fine graining in this case of an underlying graph, right?
Mhm, mhm.
You just started with a graph, you then introduce more vertices because you
I think you're
stretched
right.
the
Yeah,
graph on
yeah,
in the end.
yeah, yeah, yeah. That's right. So you're making something that has uh, it's using the topology of your original graph and just adding more vertices in communities, probably. Yeah.
Or can you do it the other way around? Take the fine graining procedure, maybe some mesh refinement on graphs,
Mhm, mhm,
and do those. How those will stabilize the graph on sequence
mhm.
if you
It's an
have an
interesting
actual
idea.
sequence.
Yeah, it's an interesting idea.
Well, unfortunately, we've run out of time,
Yeah.
and I have a hard stop. Not to sound like a therapist or anything, but
No, no, no.
I have a hard stop at the
The
top of the
session is
hour.
over. Do we
It
feel
is.
do we feel better? I don't
I
know.
was joking to some. I was joking to someone that it's become like one of these psychoanalysts because I tend to like things tend to at least reach some sort of a lull at the top
Mm.
of the hour quite often. Yeah, do we feel better? I don't know. Um,
This is that it turns binary to unary, and you would think it's simple, but look, it's giving all of this stuff. Anyway,
no, I've stopped presuming that anything is basically simple. Don't worry.
if people want to
Um,
check these out, this is the so-called Markov algorithm thing, which you can, yeah, it's rewriting plus some sort of special ordering and rules, but we obviously do multi-way, but they have some interesting examples, and so that's why I look at it. And you can make Turing machines and things out of them.
well, I'm glad to see that you're applying. You're taking many kind of well-known examples and trying to get these
Examining them.
matrices for them. Yeah. I mean, unfortunately, it seems like in the absence of some stretchy hero, most of these are just going to fall right into the void of the empty graphon.
Stretchy here. Stretch Armstrong.
In the context of causal graphs, it would also mean we are looking for a total order of our events, right? If we
Hmm.
are if there's some reducible behavior in the system, and total order is also corresponds to some kind of reference frame,
Exactly.
so we are looking like for a reference frame of our underlying
System, yeah. I've made this point before
history.
that the graphons kind of have an observer theory connection because of this ordering.
Yeah, if
Yeah.
it have a nice limiting behavior, we can say something about that it's a good reference frame that reduces our behavior of the system.
Hmm.
So that we don't have to fine grain it indefinitely. We just have a limiting behavior that we can also describe in this continuous case nicely.
Hmm. Yeah, it's nice. All right.
All right, gentlemen. Well, I must depart. This has been a good review of things that have been done recently. We'll of course continue to chat. I just desperately want. I just have these basic questions about even moduli space of
Hmm.
graphons, and I mean just to pose one other kind of question, for instance. So it's like, you know, take some graphon that we've seen in the literature, like especially this one, for instance, where it's very dark in the in like the upper left hand corner, and then
Hmm.
then it becomes
Yeah.
lighter, and then at the boundary it's basically white. So imagine that one. Now it can't be, you have to find some other graphon that has a distance from that one that is greater than epsilon. So then the question is, can you have one where it's, it's like it's darker farther to the right, or it's more that, or it's kind of more concentrated in the left hand corner, et cetera, et cetera. Do these at some point, if you keep doing that, if you kind of say, okay, we're gonna take this particular graphon where you have the values concentrated in the left hand corner, we're gonna start to distribute them out. Well, at some point, you're gonna hit something like uniformity. So you're kind of gradually adjusting this graphon. At some point, it's just going to become uniform. And so I'm trying to understand, how much you take some well-known graphon, how much can you kind of adjust it where they're distinct graphons. You can imagine over a moduli space kind of progressively changing the graphon. At some point, you're probably going to hit emptiness or uniformity. And this is why I was posing just as a kind of a how should I say it, kind of a provocation, just this idea of there being like, you have the empty graphon and the uniform graphon, and you can imagine kind of taking some well-known graphon and slightly changing it. At some point you'll hit one or the other. And I can imagine in the simple case, whatever the kind of geometry is of this moduli space, that the fact that you will often, if you're changing the graphons in a liberal way, you'll often hit uniformity or emptiness. That should have some consequence on the geometry of this thing. The fact that you can hit those particular points quite often, more probabilistically than you'd hit these other ones. It's like, okay, what would the geometry look like if you were changing the graphon too much, you're going to either make it sparse or you're going to hit uniformity? How would that actually inform the geometry of the thing?
My answer to that was, adding, given one graphon, if you keep adding Dirac deltas to it, you're sort of moving it. You could take the zero graphon and just keep adding Dirac deltas until you get to, the fully connected graphon. So it's zero everywhere or one everywhere. And you've taken that step by adding an infinite number of Dirac deltas to the domain. But at each point, you would have to sample an infinite number of vertices to even see this one extra vertex. But that's lost because you're already in countable infinity land. It's starting to make me think a little bit about, the surreal numbers. So it's like, and it was based on these graph games where one of them was called Hackenbush or something. This is all Conway stuff, right?
Conway stuff.
Yeah. So it's like, we can go from countable to uncountable, integers to reals, but surreals give us a whole universe, a whole landscape between 0 and 1 over infinity. And it's all about, defining these games on graphs and counting these games on graphs. Is there something there? I think there is, because graphons is just one avenue of extremal graph theory. It's maybe not the only one. It
might not be the only one, but it's one that has a geometric intuition, which is I think why we're attracted to it.
For the moduli space, yeah. Sure, exactly.
So this is something that I crave personally. It's some, at least intuition regarding what the moduli, even of graphons in general, would look like. I still don't feel as though I really have it.
Well, I mean, the other thing is, it's reduced to a question of functions rather than once we've arrived at the decision we're going to use graphons, you can then start thinking about moduli spaces over functions, which is tricky. Well, of a particular under particular constraints. Because let me see. Because we can only sort of look at a distance between any pair of things. I think that's why I was performing that embedding. It doesn't have the same idea of a sort of configuration space that, say, the moduli space of triangles does, or tropical curves of genus 1 or all these kinds of things. It doesn't have the same, but it does allow you to do this deformation theory thing, which is kind of the question you're asking. Like, you know, if you make small changes, that's the question you're asking there. But it doesn't give you a configuration space where you can say, oh, there's some degenerate points here, or this is the boundary here, or we need to remove this point from the middle because it completely messes up our space, you know, which they have to do in the triangle case from the literature that you gave me in the beginning. This example, yeah. We don't kind of have that problem. We haven't quite got there yet because we're still just like, oh, it's functions, which gives us this yet again another infinite landscape where we can start, I said before, like, yeah, how many functions are there from the 0, 1 squared to 0, 1? I mean, yeah, it's obviously an infinite number, and they can take on many forms: piecewise, closed form. You could use some differential equations. You could whatever. You could, like you could take the 2 parameters of this function, and they could be the initial conditions for some dynamical system that you run for some while, and that's your function. You know, just get creative. You can come up with anything. And actually, that was why I was looking at that decidability. Where was it? Yeah, it was actually undecidability of linear inequalities in graph homomorphism densities. This is exactly the same kind of. The purpose of articles show that even the most elementary problems in asymptotic extremal graph theory can be highly non-trivial. So
it's encouraging.
We have our work cut out for us, but we can end on this nice nice graphic.
Yeah. Well, thanks, guys. We'll continue this conversation even later tonight. I have to go for now. See you soon. Cheerio.